Okay, going to do a quick notes review of the sun unit for astronomy class at Grady High School. Well, the sun's a pretty average medium-sized star that happens to be yellow in color. The light that it emits, the black body curve peaks in the yellow, and that's the reason we see mostly yellow light. We spoke about this in the light unit. The density is more similar to a Jovian planet, not quite as dense as a terrestrial planet overall, but if you look at something like the core, then it's definitely more dense there. But we have to look at the entire volume overall. Rotates differentially, just like a Jovian planet, which means that it rotates faster at the equator and slower at the pole regions, and that difference is a couple of days. On Jovian planets, it was a couple of hours or an hour, but on the sun, it's a couple of days just because of the pure difference in size. Black body curve of the surface is about 5,800 K. That's the photosphere that we're referring to. These are your basic layers, starting with the core. We're going to go over this again. The radiation zone immediately around it. Radiation, just heat energy out directly. Reaches a certain point where the plasma in the sun will start to convect. When this convection hits the photosphere or the visible surface of the sun, this causes granulation. Directly above the visible surface of the sun is the first layer of the atmosphere called the chromosphere. And above that, you have the second layer of the atmosphere known as the corona. The transition zone is just an area that's kind of where does the chromosphere stop and where does the corona start. So the sun is yellow. This is basically what it would look like if you could stare at it without going blind, which I don't advise that you do. We had to quantify the amount of light output that the sun puts off, and we call this light output generation luminosity. It can be calculated by watts over meters squared. So you literally get a square meter detector, and how much energy comes in on that square meter per second. That's not that important for the sun unit, but for the following units it will be more important. So it generates energy via nuclear fusion, and that's the only way we can figure that it calculates or generates that much energy, because it generates a tremendous amount of energy. The numbers here just kind of are interesting in that 0.2 megawatts per kilogram per second. That's not a lot of energy, but if you take into account that the sun has a ridiculous number of kilograms, that 0.2 megawatts per kilogram times a gazillion bajillion kilograms equals a lot. And basically what the sun is doing is just constantly converting matter or mass into energy. This is what the famous equation Einstein gave us said. So you have nuclear fusion. Nuclear fusion occurs because the sun has the ability to overcome Coulomb's law. Coulomb's law is the law of opposite charges attract and like charges repel. So normally what you can see here is normally these two protons will stay away from each other because they're like charges. If you get conditions correctly in the universe where that can be overcome, then protons can be combined. This becomes present, or I guess it is present in the core of the sun, and you need two conditions, and that would be has to be extremely dense, which the core is, and it also has to be extremely hot, so the protons are moving around rapidly. Both of these situations are satisfied by the core of the sun. So quickly you can see these two protons here symmetrically happening down here, because we're going to need particles from this down here, but just kind of stay with me up here. These two protons will combine in the first of three collisions. this collision will occur, forming a deuteron. Deuteron is heavy hydrogen. It's hydrogen with a neutron. So one of the protons turned into a neutron. Well, doesn't work as easy as that. When this collision occurs, a positron is shot out, and a positron is antimatter. And when positrons react with regular matter, which in this case is an electron, it'll create a violent explosion called a gamma ray. And this is how the sun produces gammas. This will exit the sun, exit the core region, and be gone. In the process, a neutrino is also made. A neutrino are near massless, weakly interacting particles. They just fly out of the sun, no consequence. Now back to the deuteron. The deuteron will smash with another proton in step 2. In step 2, this will form helium-3. So no other byproducts are made except for energy in this stage. So you have the deuteron, which is a proton and a neutron with another proton. And these simply combine into a helium-3, which is an isotope of helium because helium-4 is elemental helium. Remember I was discussing earlier how this symmetrically is mirrored down here. Well, the entire process needs to be mirrored down here so we can have another helium-3 here. This helium-3 plus the helium-3 we created up here will collide in the third collision. In the third collision, helium-4 is created. So really a particle with an extra neutron is generated on this side with energy, of course. This unaccounts for 2 protons that are spit out. These 2 protons that are spit out will start the entire chain reaction over. That's why this is known as the proton-proton chain. This basically reviews what I just went over with you. Stars need to reach a balance known as hydrostatic equilibrium. This balance is between gravity and energy pressure generated outward. When energy is being created, it kind of, if you think back to an explosion, right, it wants to go outward. This will balance between the gravity wanting to pull inward, and the star will pulsate slightly in a stable manner for a long time, depending on the size of the star. That basically just reiterates what I just said. Helioseismology is the study of sunquakes, and sunquakes allow us to have a little bit of insight into the interior of the sun, just as P&S waves from seismic waves causes us to have knowledge of the interior of the Earth. So when we have these sunquakes, we're able to track the energies through the sun at different speeds, and it slows down. Sometimes the quakes don't make it into the interior zone, like this is the radiative zone. They'll only bounce around the convective zone. Sometimes if it's a stronger sunquake, it'll go through here, but we don't typically see them go through the core. In fact, I don't think we've ever seen them go through the core. Just kind of gives insight into the interior of the sun based on the speed of the wave and how it changes angles and so forth. Actual photo of a sunquake. And check my YouTube channel for these same videos that we saw in class. Just a brief descriptor of all the zones. So you have the layers starting with the core. Again, I hit this a while ago. The radiation zone immediately after, then the convection zone, the photosphere, chromosphere. The chromosphere is this first little atmosphere that's denoted by these what's called spicules, and then the corona is this outer atmosphere. Rotates at different speeds. I already mentioned that. It also rotates at different speeds within the sun. We believe the radiative interior rotates uniformly, almost like a terrestrial planet. About 26.9 does. So the core is the engine of the sun. That's what's doing all the power generation. Has a density of about 20 times that of iron. The core accounts for 90% of the sun's mass. And inside the core, you have 15 million K temperatures. Whereas only 10 million are needed for nuclear fusion, 15 is a little beyond what we really need, but it's plenty to get the job done. Just another shot at this. The only thing that I really like about this diagram is the fact that it shows the different sides of the convection cells. Convection cells closest to the radiative interior will be larger, and as they get further and further outward, they get smaller. And then these little small convection cells in the outer surface will cause granulation of the photosphere layer. So in the core, it's hot and dense. This is what I was talking about with fusion. This leads to a lot of particle collision. Because it's dense, there's lots of particles everywhere, and because it's hot, they're moving fast. Gas is completely ionized in the core, so there's no photon or light energy being created in the core. It's just heat energy. Because if something is ionized, that means electrons have separated from it. If you remember back to the light unit, we need electrons to generate light because they need to jump up and down energy levels. We'll start to see photons being created in the radiation zone. That's not where most of the photons are released. Most photons are released in the convective zone, especially toward the surface where the photosphere is, because that's where electrons are allowed to kind of stick with atoms and not be completely ionized. Convection cells, after you get through the radiation zone, convection will start to occur within the plasma. Plasma is a fluid, so that shouldn't be that foreign an idea that convection takes place. It's physical movement of the plasma particles. If you look at this diagram up here, you can see that as the convection gets closer to the surface, right, it's carrying the energy up here, and then it's lighter in color because it has the photon energy, and the photons will release and go flying off to the Earth and the other planets and throughout the entire galaxy. And as it releases those photons, the plasma cools, gets denser, which that's the reason it darkens, and then it will sink back down, and then we'll continue this process. This causes granulation of the surface. So convection cells are visible via the granulation, and this is another basic way to prove that the convection zone is a real thing and not just theoretical. We can actually see the granulation zones. Chromosphere is the inner part of the solar atmosphere, directly above the photosphere. It's about 1,000 K less than the photosphere, which that makes sense, right? As you get further away from the core, you would think it gets cooler, and that's correct in this sense. It's a great shot of the spicules, right? The little mini storms. I like this diagram a lot. These little mini storms right off the surface. It's nothing as big as the solar flare, but still visible. So this is a good shot of them. Evidence for this is from solar telescopes. Not on Earth, we see absorption lines in the spectra. Shouldn't be absorption lines if there's no atmosphere absorbing them out. So, the corona is the outer atmosphere of the sun. It's only naturally seen during an eclipse. We artificially study it using what's called a solargram. Gas in the corona is super duper ionized. As it loses electrons, spectrum appears different, and we actually identify it as its own spectrum called coronium. For some reason, which is still unknown but theorized, lots of theories about this, the corona is way hot. About 1 million K. If you remember back to the other temperatures, that's way hotter than the photosphere or the chromosphere. So for some reason, this outer atmosphere of the sun is exponentially hotter than the surface of the sun. So magnetic disturbances on the surface are believed to carry plasma, inducing heat up into the corona. That's the best theory we have right now Honest answer is we don't know. When corona particles are gravitationally released from the sun or no longer bound to the sun, these are kind of whooshed away, if you will, in a process known as the solar wind. And it's basically a stream of particles, mainly electrons and protons. They tend to be high energy because they're ionized because they're so hot. And they kind of whoosh out in this kind of weirdo pattern like this because they rotate at a differential rate than the sun itself. So at some point they become gravitationally unbound and they fly out. Now this causes, if you can see in the background, this causes interactions with planets, especially if you don't have a magnetosphere. It causes issues. Luckily for us, we have one that causes auroras on our planet. So this kind of shows temperature scale based on distance above the photosphere. So here's sea level at the photosphere, right? It's roughly 6,000, and then as you go a little bit further up, right, this is the chromosphere. You expect it to get cooler. Then as you get into the transition zone / corona, the temperature goes up exponentially. Again, kind of unexplained. We're just collecting data. Sunspots. Sunspots are darker regions on the sun. They're darker because they're cooler than the photosphere. They're about 4,500 K. That's still hot enough to melt your face off. But compared to the photosphere, it's significantly less temperature. You have two identifiable regions. The central area, which is darker, is identified as the umbra, and the outside around it is called the penumbra. If you remember back to eclipses, we had that same terminology. The darkest region of an eclipse is the umbra, and the not as dark is the umbra. So here you can clearly see umbra, penumbra. This kind of shows just a time lapse of the sun rotating. You can kind of see these sunspots in this location, and this location, and also in this location, this location, this location, this location. So this is showing that the sun rotates, which Galileo noted by collecting data on the sun himself. Now, sunspots occur in pairs, and they occur in this interesting pattern based on magnetic field lines of the sun. Here you can start off, if you watch it here, it's north-south. This one's also north-south. Well, as the sun continues to rotate, and again, you got to remember it's rotating differentially, so it's rotating faster at the pole region, not the pole region, the equatorial region. So what happens is the south sunspot will start to lead the north sunspot on the northern hemisphere, and it's vice versa on the southern hemisphere. The north sunspot down here is leading, and this will cause these things to loop over as they get down to here. This is basically exactly what I was just saying about why each hemisphere has a leading polarity. It's opposite to what you would normally think. The north hemisphere leads with the south sunspot. The south hemisphere leads with the north sunspot. The magnetic field will loop, just as any magnetic field will, from north to south pole. On the surface of the sun, plasma will actually ride these loops, and it'll cause these really large things right here, right? These large loops of plasma. Now they have a name as well, which we're getting to. Sunspots go through a cycle. This just kind of shows where they tend to be latitudinally. I'm not sure if that's a word. As it goes through the different cycle, right? It gets closer to maximum, they appear to be closer to the equator. Minimum, they get a little bit further away. This is because of the field lines. The sunspot cycle is 11 years. Now that's going from minimum to maximum. The entire complete cycle is 22 years from minimum to minimum. On the test, everybody wants to know this, on a test or any kind of assessment, I want to ask you what the sunspot cycle is going to be. It's going to be 11 years. It's not a trick question. The sunspot cycle is 11 years, but that means from minimum to maximum. The Maunder minimum was a period in the late 1600s to 1700s where there was like a period of almost complete shutdown of the solar cycle. We're not exactly sure. It's not complete shutdown, as you can see, but it was not as regular as the rest of this data kind of shows. Another little period like that in this region here. So kind of confused as to what caused that. We have no idea. Data collection not the same as it was back in the day. So solar prominences are these large loops of excited gas that form the surface in active regions. So what's an active region? Sunspot could be an active region. Oftentimes prominences will loop from one sunspot to another. Now this is not your typical prominence. This is a really large one. You have two different types. You have quiescent and active. Quiescent prominences last for days, sometimes weeks. This was a quiescent prominence that lasted for almost a month. And this was on the news and it was quite well documented. Active prominences come and go. They're very erratic, short-lived, and they're typically associated with sunspots. Easiest way to think about prominences is they tend to be loops, right? So, solar flare is oftentimes referred to as a bomb, a solar bomb. It just suddenly explodes in an erratic fashion. You really have no idea it's even coming and just kind of explodes off of the surface in one direction. These, more often than not, are from sunspots. The last type of solar storm that we're going to talk about are coronal mass ejections. They're oftentimes referred to as CMEs. And they are giant magnetic bubbles of gas. They are a super mega atomic solar flare bomb kind of thing. So it's more like a solar flare in the way that it kind of explodes and is a little more erratic. These are a little bit more dangerous to Earth because they can overload electrical substations, can cause power outages, and they've done that before, can disrupt cellular networks and so forth. So these are things that astronomers watch quite a good bit. Space weather guys. So they are seemingly can be dangerous to the planet. They occur 1 to 2 times a day during solar minimum, 10 times a day during solar maximum, as much as that. Has to be directly in line with planet Earth in order for that to impact it. And the odds of that happening are not great because the sun is a sphere. And of course the planet and the sun are moving all the time. So got a lot of things adding up to not equal a lot of CMEs hitting. Last thing we're going to talk about is neutrino observation. This is a neutrino observatory over here. It's called Super Kamiokande. It's in Japan. Neutrino observation is an important way to study the sun because, well, we know they form during nuclear fusion, and this is a great way to explain that the sun is using the proton-proton chain like we're theorizing. So we like to study that. They also form in supernovas, hypernovas, active galactic nuclei, which is a very young galaxy. We'll talk more about that. First design experiment was in South Dakota in the 60s. This is in a gold mine, and the reason is that is you have a lot of dirt interacting, and it kind of eliminates a lot of data that would not be accurately portrayed. So, such as cosmic rays, and cosmic rays are just stray electrons and protons that are always coming into the planet from the solar wind. In this experiment, they used chlorine-37, which is an isotope, and they were trying to get neutrino to interact with this and convert it to argon-37. Should have caught one a day. Really only caught about 2 per week. This was kind of a big question mark. We didn't really understand why. We later found out why, but at this point we didn't. So they designed another experiment called the Galax probe, which uses gallium, which is a little more interacting than chlorine. It also didn't catch as many as we thought it would. The Super Kamiokande in Japan, which is the one I showed you the picture of a minute ago, used deuteron or heavy hydrogen and big old giant tanks, like larger than a swimming pool full of deuterium or deuteron, and it produced the first visible image from a neutrino observation, causing Cherenkov radiation through the tank. This is actually an image from the detector. As the neutrino kind of went through this way, you can kind of see the wake that it made, much like a boat. So that's what that's showing. This is the newest neutrino observatory. It's called IceCube. Kind of a joke name, but these are the photo detectors here. You can see how big this thing is compared to the Eiffel Tower. This is in Antarctica, and these holes are drilled, and then these photo detector tubes like this are put down in here, and they're hoping to catch neutrinos coming up through the bottom of the Earth, hoping to give it a little more shielding from cosmic rays. So this is what I was just discussing. It's currently under construction. It's not finished yet, but it should be finished in a couple more years. They're already collecting data on it. This is data from the IceCube right here, again showing Cherenkov radiation, which is basically the interaction of the light particles through the ice, and it's kind of showing the direction in which the neutrino is traveling. Another detector was called the SNO, or the Sudbury Neutrino Observatory. This is the first one to capture the estimated amounts of neutrinos. So the problem was we were only catching about 1 in 3 that we thought we should have been catching, and this one, it was in England, and this is it right here. It's no longer in operation. The detector was sensitive to all types of neutrinos, not just the VE. Neutrinos come in 3 varieties. We didn't know that in the 60s, so now we're a little bit more wise to that. So here are the 3 types of neutrinos. The previous ones were only looking for the electron neutrino, but now we realize that there are the muon and the tau neutrino, and the new detectors, such as the Sudbury one and the IceCube, are able to detect all 3 of these types. So, all right, that's my notes review. Hope you enjoyed it. Study up.